now we're going to talk about the group law on an elliptic curve. So here's how we define the group law in general for an elliptic curve. The geometric definition of an elliptic curve, of a group law in an elliptic curve, it actually can be done for generic cubic equations. It doesn't have to be on a Weierstrass form. So let me first say, how do you define the group law? So first, some cubic form will look something like that, okay? And it comes with a point, with a rational point. So I'm going to put my rational point, I'll continue that like that a little bit. And here is going to be my point O. Okay, so if I have 2 points, I hope that's going to look okay. Yeah, so if I have 2 points, P and Q, I want to define an addition. And here's how we define it. First, let L, so this is my elliptic curve E. So L is going to be the line that goes through P and Q. Okay, so draw that line. And then that line will intersect at a third point R. So it will go through a third point because the equation is cubic. Okay, so this is given by a cubic form. And then that is not going to be P plus Q. What we're going to do now is draw the line. So this is the line L. And now I'm going to draw the line through R and O and find the third point of intersection. And that is the point I'm going to call P plus Q. So, so now L prime is going to be the line through R, O, and then it has to go through a third point, and that is going to be P plus Q. Okay. In general, though, that's what happens in general, how you would define the addition in general, but we actually like Weierstrass models, and in particular in Weierstrass models on in short Weierstrass models, they look like this. They look something like this, and the way you define it is that, well, first of all, you pick O to be the point at infinity, so O is somewhere here in this case, okay? And if you have 2 points, P plus Q, here and here, let's say, P and Q, then you do the same definition we've just mentioned, okay? So I do the line through P and Q, that intersect at a point R. Now I want the line through R and O. What line would that be? Well, if you remember back like several lectures ago, every vertical line in the projective in the affine space, every vertical line, when you look at projectively, goes through the point O, goes through the point 0, 1, 0. Okay, this is 0, 1, 0 in projective. Every vertical line goes through it. So there is one line that goes through R and O, and it should be that one. So it has to be a vertical line. So it turns out that all vertical lines end up going through O. Okay, and that line will intersect your curve at a third point of intersection, and that point of intersection is what we call P plus Q. Okay, so that's how we define the group law. And so here is some key to all this, to the properties of the addition on a short Weierstrass model or on a Weierstrass model. the key is that the tangent line at O is the line z equals 0, and it has a triple point of intersection at O. Okay, that's because if the tangent line is z equals 0, there is only one point on the curve with z equals 0. But a line and a cubic have to intersect at 3 points. So if there's only one point, there has to be a triple point of intersection right there. Okay, that is not true in a general cubic, but in a short or in a Weierstrass model, not short, just in a Weierstrass model, that happens. That z equals 0 is a line that is tangent and it has a triple point of tangency. Okay, great. So you can you can check yourselves that the tangent line is z equals 0. You can just look at the gradient or just take the derivatives, find what the tangent line is, and you'll find that it is z equals 0, and there's only one point of intersection. This gives you the following proposition with the following properties. So part A, if O is an inflection point, meaning that at O, the tangent line has a triple point of intersection. And if L intersects E on P, Q, and R, then P plus Q plus R adds up to be 0. Okay, you can see that you can see by in the picture that I put here of the Weierstrass model, it is clear that that happens just by definition of the how addition works. Okay, B says that P plus O is P for all P on E. So you can see that, for example, if you want to add P and O, then what I would do is first trace the line from P to O. That is going to be a vertical line. So the vertical line is going to go through O and find the third point of intersection, right? So the third point of intersection will be here. And then you have to find so this would be my point R, and then find the line from R to O and find the third point of intersection. But the third point of intersection, then it will be the same line again, and it will be this point that you get back. So you get P again. So that's why P plus O equals P. Right. How about C? P plus Q equals Q plus P for all P and Q on E. That is because the definition of the line that goes through P plus Q is the same as the definition of the line that goes through Q on P. So it is abelian. D, for all P on E, there is a point that we call minus P on E, such that P plus minus P is O. In this case, in the case of short Weierstrass forms, the case of P and minus P. So if P is X naught Y naught, then minus P is X naught minus Y naught. That will be minus P, because P plus minus P will give you the point at infinity. By the way, why is it that P plus minus P gives you O? Well, if I do the line between P and minus P and find the third point of intersection, that will be vertical and gives me O. And now I have to do the line through O and find the third point of intersection. But because O is a triple point of intersection, the line through O and O is tangent, and the third point of intersection is O again. So I get O. So that's why P plus minus P equals O. Okay. And E, P plus Q plus R equals P plus Q plus R. It is associative. This is not clear at all, and I'm not going to prove it. I'm not going to prove it because later on we're going to prove associativity in a better way through Picard groups, and it's quite messy. I challenge you to draw an elliptic curve and do all the lines to do the addition of P plus Q equals R, and then add P plus Q and R to get O, and then do it the other way around. Add Q plus R, and then add P, and check that you have the same, sorry, R is a different point here. So it's not the R that appears in the definition. So you take 3 different points and add P plus Q, then R, then add Q and R, and add P, and show that they're the same. Graphically, it's quite a challenge to actually make a graph that will show this. So this is for all P, Q, and R on E. But again, this associativity, we will prove in another way. And finally, F, by the way, up to here, this proves B, C, D, and E shows that this is an abelian group. And the last piece is that over K, over the field of definition, this is a subgroup of E. And I think I'm out of time, so we will talk about that next time. So again, so this shows that it's an abelian group, that E K bar is an abelian group. Part F shows that over K is an abelian group, and we'll start there next time in class. All right, bye.